Thanks, Tim. Tēnā koutou, e tēnā ia iahi, ko Ewan Rodaway aho. I'm going to be talking to you about evolving freshwater management in the face of intensification and climate change. So this is primarily about the way in which Southland have managed our freshwater resources, particularly with regard to allocation, and what we are doing to evolve that management in the face of some pressures that we're seeing from either a changing climate or increasing demand for that water use. So there's some acknowledgements for this work. Most of this that I'm talking about is part of joint and co-funded work with GNS and NIWA, and the project leads for this work are Lawrence Keys at ES, Christian Zammit at NIWA, and Catherine Moore at GNS, and there's a large number of people in each of those teams at their respective organisations. So a bit of an overview. I'm just going to touch on some of the historic management methods that have been used in Southland, some of the issues that we are currently facing, and then the realisation that we needed to move to better characterisation of our systems and perhaps the development of more complex models to help us solve some of the problems. How we are combining these complex models with management tools for our everyday use in council business, and then bringing it back to the theme, I'll talk about resilience in the face of increased demand and climate change. So I've got this diagram here to try and talk about the methods in which we use to manage water in Southland. Generally it's sort of a package deal of a overall allocation of a resource combined with an assessment of localised effects. So I've just got this diagram. You can imagine the large blue box is our calculation of what our overall resource might be, and within that there is an allocation limit depending on what the resource is that we set. Some amount of that is consented, and then and again in that some amount is actually used. And so there's a whole lot of historical data and information that goes into making these calculations. So we could assume that maybe this is a groundwater resource. We have estimates of recharge that can change depending on many things, estimates of discharge from that. And to go with that overall allocation, we have the localised effects side of it. So I've drawn this well in here to try and describe that. So we may have a good idea of what the stream depletion effects are, for example, associated with that well, or what the drawdown effects are on a nearby well. But some of the issues with this method is that we often do it looking at surface water and groundwater relatively separate, and we also sometimes struggle to capture the full cumulative effects of all the takes that are going on in the system, both over a large catchment scale, for example, and also over longer periods of time. So whilst this has been pretty good, now that we are seeing extra pressure from a changing climate and increased use, there's very little fat in the system, and we need to move something that is both a bit more transient and can better look at those cumulative effects. So this is just an example of one of the issues that we're grappling with in Southland. This is a graph of groundwater level in the Edendale Aquifer, so in eastern Southland. This is an envelope plot, so the envelope is the grey areas of grey here, and this is generated from over 15 years of historical data. The dark grey represents daily maximum and minimums, and the light grey represents the 80th and 20th percentiles, and the white line in the middle, which might be a bit hard to see, is the mean. The blue line is the actual groundwater trace over the last 2 years. So as you can see, through 2016 we were pretty close to the mean and within the normal range. But as we get through to the winter of 2017, we had quite a dry winter, and there was actually a very delayed recharge period in this, or delayed recharge in this aquifer, delayed by up to about a month. And then when recharge did occur, we actually had only about half the level response in this particular bore. So as you can see, the level only came up by about half the amount that it normally would. And the result of that is that it's offset from then on, and even though we've had a normal recharge this winter, we're still seeing levels over a metre below what are normal in that aquifer. And that's had consequences for that community with people's bores drying up. And so what this really shows is that the seasonal variance of climate change can be really significant on some of our resources. And whilst many predictions may not predict large changes in annual averages, but there is expected to be significant seasonal variance, and again this shows what effect that can have. So what we need is really, I think Chris touched on it, the ability to build what-if tools and test scenarios. And so to do that, I think we need more transient models and ways of doing this. And we need to be able to look at it need to look at groundwater and surface water in a more integrated fashion as well. We need methods that are agile and scalable, because we don't exactly know what the questions will be going into the future. So we need methods that can help us answer questions that come up in the future. And another thing is we need something that can help us build resilience into our management framework. And by that I mean something that we can incorporate new knowledge into over time, but is comparable through time and is not lost with either changing staff or council priorities. But we can't necessarily just jump straight in from what we have been doing and to generating complex hydrological models. We need a whole lot of science in order to do that. Luckily, ES has been going through a lot of characterisation in the last 10 years with specific investigations, collecting isotope data, hydrology data, hydrogeology data, soil hydraulic data, and also broad scale but high resolution data sets, which allow us to have large scale models but be able to zoom in to solve particular problems. So for example, with the wizardry of some of our friends at GNS, we've managed to develop a regional 3D geological model. So this is a geological model of the entire southern region. This is really our source of truth for our geology and conceptual understanding, our depths to basement, aquifer boundaries. This is really the framework which hosts our surface water and groundwater resources. So the information that's housed in this is really important for doing stream depletion estimates, drawdown effect estimates. So and another example that I've got up there is Midmatara loosely coupled flow and transport model. So this is a groundwater surface water loosely coupled model, and this is developed by NIWA, and this really helps us fill in that hole of understanding surface water and groundwater and looking at them in a more integrated fashion, and also accounting for cumulative effects across a catchment. So these aren't solvable models, I guess, or they don't tell us all the answers, but they provide that regional and catchment context for which smaller scale questions can be answered, and investigations can be undertaken using the context that these provide. So one such investigation which we've been through in Southland with GNS again is an investigation in the Waimea. This was really a question around surface water and groundwater interaction. The issue was that we were seeing eutrophication in the Waimea stream, and we knew from our conceptual understanding that groundwater was probably playing a big role in this, but we needed to look closer to see. So we undertook a FODTS study, which is a distributed temperature sensor, basically a long temperature sensor which is laid out in the stream, and that can detect different changes in the temperature of the water and detect where groundwater is entering the stream. And this was combined with taking water samples and looking at the hydrochemistry. So what the temperature sensing told us was that most of the groundwater was actually coming in through side tributaries and springs rather than through the bed of the stream, which we initially maybe thought. And when we combined that with the hydrochemistry, we were able to see that all of the nitrogen almost was coming from these tributaries from this area of land here, which had a high nitrogen leaching risk, or high risk of nitrogen loss. And compared to these areas of land here from the tributaries to the south west, where almost very little nitrogen was coming. So that really generated or filled in some knowledge gaps that we had for that particular area. So one way in which we're taking these complex models and trying to use them for our everyday business is to use another tool developed by NIWA called CHES, or Cumulative Hydrological Effects Simulator. So that can take the naturalized flow from a flow model like this, and then it can use that and generate a stream depletion effect anywhere throughout the catchment. And that actually takes into account those groundwater depletion or cumulative groundwater effects on surface water. So again, it helps us fill that hole. Okay, so some lessons learned. Models certainly don't give us all the absolute answers, but are really good for indicating relative change or change in direction. And they give us that ability to test different scenarios. So bringing it back to the theme of resilience, I thought if we don't have a resilient water resource management or resilient water resources in Southland, what are the major risks that Southlanders face? Is that current users would be cut off due to a change in availability and a drastic change in management, or that ecosystems are being cut off from vital supply due to over-extraction, or perhaps the quality is degraded to the point where ecosystems and users are affected. And these methods that can really help with improving resilience in our systems, because like Chris said earlier, they give us that ability to plan and to incorporate change into our estimates of the effects that we're having. So to incorporate the changing climate or the changing land use into the effects, the estimates that we're coming up with. It gives land users much more information to make good decisions about how they use their land and hopefully build resilience into their business. And again, it provides ES with a resilient management framework, so we can pour our evolving knowledge into that. It's consistent through time and it doesn't change as the council or staff changes as well. So I think the take-home message is a better understanding of our systems and ability to plan means that we can be more confident in what we can and cannot do with our freshwater resources. Thank you.